Okay, so welcome to this video on getting started with programming in Scratch, and this is the first of several videos. In this video, I'll just sort of give you a little bit of a background on programming in general, and then also get us oriented, I guess, with Scratch. Um, and then there'll be other videos to follow of doing sample projects and things like that in Scratch for you guys to use as examples as samples, I guess, for the project that you're going to do. So this, I'm sure, will be the the most fun part of the course. Not that doing binary numbers and logic gates and whatnot isn't fun, but making a video game is probably a little more entertaining in a lot of ways, but is definitely more challenging in others. So. But I think it's a good opportunity to exercise what for some of you maybe will be a more fulfilling task where you can kind of use your creativity and do all these other things that have probably been sorely missed in the course so far. So anyway, um, these notes, I just have a handful of slides here at the beginning just to kind of give you a sense of what programming means in general. And then we'll get to the Scratch piece. So just sort of consider this a little bit of an overview of what programming is, which is kind of important even in what you guys are going to do, to have a little bit of a perspective on things. So, right. So we certainly know how to make logical circuits, and one of the last things we did was see how circuitry at the sort of lowest level can be created to help a computer make decisions and to do simple tasks. So we, for example, saw how to code up a circuit that would check if a number is, bigger than 7, because when it's bigger than 7, something's supposed to happen in a computer. So, so we saw that, and we even saw how to do simple actions like addition, right? Just a simple idea of adding some binary numbers together and seeing that, okay, yeah, sure, there's a logical circuit that does that. So a program, what is a program? Is just a bunch of simple instructions that a computer can execute in the CPU, and it'll execute it by doing the similar things that we did before with logic gates and logic circuits, and checking, is this number 4, is it time to do this yet? And then doing the very basic operations that we described, basic arithmetic and things like that. So that's really what a program is at its most basic. Now, how do we sort of rectify that, I guess, with what our sort of everyday notion of what a program is? Well, I think our notion more so of a program is software, right? If you use that general term, software is, a product that you buy or download or something like that, that does something on your computer. Maybe it's a game, or maybe it's a Microsoft Word or something else, right? That's a program, or that we could call that software. And it's the same idea, but of course, very, very complicated, as you might imagine. So how do we sort of communicate when we think about a program? How do we sort of communicate with the computer? We've talked at the very lowest level that this should be done with circuits and things like that, but I mean, we don't have like batteries and soldering irons and whatnot that we use in order to communicate with the computer, right? We sort of do so at a higher level. So what's the sort of hierarchy of all of this? Well, I said this already. So just because this is an adorable picture, I had to sort of put it in here. The sort of evolution of the idea of software, right, and of programming is that, of course, we want to try to be able to communicate with a computer. Now, very early computers, if you look at this picture down here, were mostly just, sort of what you see in this picture, which is a bunch of wires and some batteries and some magnets and things like that. And this literally is, I don't know where I can't remember exactly where I grabbed this picture, but as you can tell by the outfit of the woman in the picture. This is a very old, and is a picture of one of the earliest computers from probably this is from the 40s or maybe 50s. And this computer, which as you can see is enormous, was basically just a big adding machine, or a calculator. So something that now you can buy for $3 and is the size of fits in your palm, used to fill multiple rooms to mostly just do addition and subtraction and things like that. And how did you sort of communicate or tell this type of a computer what you wanted it to do? Was that you would create your program, you would punch it into a card, right? So this little picture down here in the left corner is an early example of software or of a program, and you can probably see little spots on here where the green is showing through. That's where someone, a programmer, physically punched some holes in the card to represent zeros and ones, right? So where there's no hole is a 1, and where there is a hole, there's a 0. And believe it or not, right, the sequence, I don't even know if it was fed left to right or up and down, I'm not sure what order, but this would be fed into one of these sort of archaic machines like this, and it would read the holes or the non-holes, and it would say, oh, okay, that corresponds to some binary code that means, move this number over here, or something like that. So obviously this was very primitive, although this technology of punch cards, as these were called, really was the early format for what software was that existed through the 50s and 60s, and even into the early 70s, before we got a little bit better with how to communicate with a computer. So what language do we speak in, so to speak? Well, the computer, and this I still mean for computers today and your phone and anything else that's electronic, only speaks one language, and as you might guess it, the language it speaks is binary. And now we've used the word binary an awful lot to refer to numbers, zeros and ones for numbers. We used it for logic to talk about on or off, or true or false. And in terms of a language, machine language is the term that's used to describe the lingo, so to speak, that the computer understands. So, not surprisingly, right, it's binary, and it is zeros and ones. Now you may say, okay, what does that mean? Well, for example, I think I just made most of this up, but when a computer, again, and I'm not talking about the one in this picture, with this lady from the 50s. I'm talking about the computer that you're listening to me on, that you're listening to this video on right now. Only speaks machine language. It only speaks binary. So whatever your computer is doing right now, it's playing a video, right? It's playing me. It's doing so by having you're probably watching this in Canvas, right? So Canvas is a program, of course. So Canvas is speaking to actually Yuja, which is where I upload these videos. And they're talking to each other, and they're saying, oh, okay, play this video, and play this video, and play this video, basically. But they're not saying, play this video. They're saying 0100100100100, okay, right? All binary stuff. That's machine language. So that's how computers talk to each other. That's how computers talk to servers. That is the only lingo, right? There is no alternate language that computers understand. Everything that it's going to do must be presented as binary. And when we're talking about code or talking about a program, we call binary machine language or machine code. Okay, right. And so as you might imagine, tasks, right? Things like loading a number into a certain memory spot. Each task, or in this case, each component of this task, has a binary code associated with it, right? None of this is important, right? But I'm pretty sure I just made this number up. But let's say whatever this enormous binary number is, when the computer gets that number, it says, oh, that means load. That's the binary number 5, right? 101. And this is some memory slot. I think that's correct. That's the binary code for the number 27. So if we were to see this sequence probably with some things in between them to sort of say, okay, how is this different than this and this? But in any case, your computer, the one you're using right now, or your phone, or anything else, would understand and say, oh, that's the code for load. And then a couple bits later is the number I'm going to load, the number 5. And then a couple bits later is where should I put it? Okay, so if you wanted to write a program, which is where we're headed with this, and we were going to code in machine language, you'd have to learn, probably via a painfully long and tedious chart. You'd have to learn the binary codes, I guess, for every command. Moreover, I mean, I don't even know what this would mean, right? Load a number into how is that going to be a video game, right? A video game that you play on your cell phone. I mean, does at some point that require you to load a number into a memory slot? Probably. But I mean, this doesn't make a video game by itself, right? I'd need like a cajillion of these sorts of statements. Okay, so if I was going to write a program, which is what we're going to try to do, machine language is probably not the level I want to come in on and say, yeah, that's what I want to do, is I want to write my code to be binary. So as a result, the evolution of, but that is how it originally was. And again, very early computers like that one with the lady were pretty much that, right? You pretty much had to speak machine language in order to communicate with a computer. Okay, we've developed programming languages, as we might call them, as a better way for humans, or programmers, to interact with a computer. So I don't have to write binary, so I don't have to physically type zeros and ones for everything I want the computer to do. Instead, I just maybe can write, sort of English, right, or a language that would say, oh, okay, I want you to load this. I could maybe just say something like load this, or something, So programming languages have evolved over the years, right? Machine language is the most basic and the lowest level. Oh, yeah, there it is. And as you sort of run up this chart here, the languages become closer and closer to English, or whatever, a spoken language. And also, they become much more. It becomes much easier to deal with languages and sort of interact with the computer the higher you go in this chart, right, up to high-level languages. So I'm going to just briefly show you examples of these three, just to kind of give you a sense of the evolution. We're going to come in at the highest level, at the 5th generation, which are graphical or natural programming languages. And you're going to see the difference between what we're going to do, which is going to be pretty easy, at least in terms of the communication, with the computer. It's pretty easy, compared to what we just saw, which was this awfulness, right? This awful, that if I want to do something, I have to look up the binary code for it, and right, it's terrible. All right, so let's take a brief tour then up this chart, and so we can maybe better appreciate where we're going to be in this. So assembly language is at least English. So assembly language is the one step up from machine language, and over here are maybe examples of assembly language. And as you can see, it's in English, first of all. I don't have to write binary. I can say things like read a number called num1 maybe, and read a number called num2, and maybe load this number into some memory spot, and maybe add the second number to it, and store the sum, and maybe print it to the screen, and then stop. Right. So it's English, so at least that's a plus. However, again, what does this little program do is it takes two numbers and adds them and prints the result to the screen, I guess. So it's not very, again, video game, right? Right, world's worst video game, if that's what, if this is what you guys turn in, is something that takes two numbers and adds them, you're not going to have a very good grade on your program. And that's right. And if I had to write in assembly language, I would unfortunately have to break down game into this basic of into lingo that's this basic. Well, this is still a little too low level for us. So we move up one more spot to what are called symbolic languages, where we're still going to hopefully be in English, but there's more than one instruction that's sort of bundled into each statement. So in other words, each line or each thing we might type in is going to maybe involve several of these sorts of assembly language statements to be sort of wrapped all into one, right? So for example, you can imagine here, right, if this is just adding two numbers, I mean, your calculator does it without needing to do, 6 lines? Your calculator can just say, okay, you type in the one number, you hit the add sign, and you type in the second number, you hit enter, and it tells you the answer. So I'd like to maybe be able to bundle some more things together. So this is an example of a symbolic language called Pascal, which, again, it's in English, and it's not super sexy, right? It's not super sophisticated, but there is a little bit more of a like, okay, here, like for example, one thing that's better is that I can interact with the user. So even if you don't know what this actually means, you can probably make a guess that this is something like print this to the screen, prompting the user to enter number one and then grab that number, and then prompt the user to enter number two and then grab that number, and then maybe compute the sum, and then maybe print the sum or write the sum or store the sum or something like that. So you get a little bit more bang for your buck, right? And sort of lumped in with that are the fourth generation, which to be honest are kind of similar. You can create objects a little bit more easily in a fourth generation language. I should be saying, right, so some popular examples, which you may have heard of, are things like SQL and Java and C++, which if you take the programming course that we have here at Endicott, the intro sequence is taught in C++, and the second sequence is taught in Java. So there is, these are contemporary languages that we still use today. And what does a language like this look like? This is a Java snippet. Is that you sort of organize your thoughts into saying, okay, if I'm going to be asking about a person, maybe I create something called a person that has some characteristics, and then I work with those objects. Okay, so this is all not super important. Where we land, though, at the top of the chart, so to speak, is this fifth generation, which are sort of comprised of two different groups. One being natural languages, which really do try to not only, I mean, I know these last couple that we've looked at, these are mostly sort of English words that you see on the screen here, but they're still sort of, I don't know, right? They're not humanish, right? I mean, you still sort of sound like a robot if you would read this program in English. It's a little, I don't know, unnatural, right? So modern, very modern and newer languages try to really be like English, like I'm speaking to you right now and using maybe slang and using other things. There's a movement to try to make languages, even ones that are, designed to sort of do these sorts of things, be much more natural and not be sort of so bogged down with sort of syntax. And there are many of these, and no one is more famous than others, but there are a number of languages out there that really try to just sort of say, like if you cut and pasted something from Microsoft Word that was a description of what you wanted your program to do, that it would try to parse that out and try to change that somehow into a program. Anyway, that's those natural languages. The other popular way to go in order to make programming more accessible, right? I mean, it'd be great if I could just speak, right? And in fact, I should say, right, the most natural or most prevalent natural language that maybe is part of your everyday life are, voice assistants, right? So if you have an iPhone, you have Siri. There's a number of other ones. There's the Google one now. What is it? Hey Google, I think you say, and then it activates a voice-activated interface, right? And the idea there, of course, being that you don't even need to touch your phone or push buttons. You can just literally speak to your phone, and it speaks English, right? So that's not exactly a programming language, but that's the idea of what natural languages are trying to do in order to make communication with your device, your phone, your computer, more human. Okay, the other popular way to go, and this is the route we're going to go, is to create programs in graphical languages. So by graphical, I mean we're going to create our programs by simply, and I guess I shouldn't say simply because it can get difficult, but we're going to build up our programs basically by using puzzle pieces that we're going to sort of drop into place. We're going to drag and drop them into place. So combining them is very easy. And the fact that it's going to sort of be idiot proofed a little bit, which is very important. If you've taken any other programming, you know it's very frustrating when you have 99% of what you've typed is correct, but you have one thing sort of out of place and the whole thing won't work. Well, for us, Scratch, which is the language we're using, is sort of idiot proof. That it's sort of impossible to cause a crash anyway. It might not do what you want it to do, but it's not going to sort of blow up or fail to run. So graphical language is very popular now in order to, again, make it easier for us to talk to the computer. So that's the warm-up, at least, of thinking about programming and thinking about coding. I should say, right, the idea, though, of any program, including the ones that you guys are going to write, is that what you have, and for many of you, I imagine this is the first time you're going to have ever written a program, it's sort of an amazing thing. On the one hand, you have sort of complete control, which is both wonderful and also a little scary, I guess, that whatever you tell the computer to do, it's going to do it, in the context of this game we're going to create, which is great because you can be creative, you can go crazy with all kinds of intricate details, letting your imagination sort of run wild. But on the other side, if it's not doing what you want it to do, it is doing what you told it to do. So I guess there's a distinction, right? If you say, I want this to bounce off the side and go into this, bounce the soccer ball off the side of the screen and have it go into the goal. Well, if you don't tell it if you don't say that's what you want it to do, it's not going to do it. So you have to sort of take ownership of the fact that it's only going to do what you say, right? Or what you code for it to do. So as we go through this, and you all have issues, I'm sure, when you're making your games of, why doesn't this work? It looks good. I think I'm doing the right thing. Why isn't it working? And that's a natural thing that's going to happen to all of us. And probably even when I make the little sample games that I'm going to make for you, I'm sure I'm going to mess them up occasionally as well. So, that's okay. Don't worry about it. The idea is that programming is a sort of scientific process where we're going to try some stuff, and when it doesn't work, we're going to revise it and come back and hopefully make adjustments, and then hopefully it'll work. So, okay, so these next several slides is your introduction to Scratch. So Scratch is the language that we're using. So what is Scratch, right? This is a high-level graphical programming language. This quote is from their website. So Scratch is made by MIT. So it was designed, about 10 years ago, I think, for as an educational tool. So which is good because that's how we're using it. I will say it was actually designed for kids. So, and you might pick up on that when you see the screen when we start it, that it was designed sort of as an outreach, and maybe some of you, in fact, were probably the target audience in many ways for elementary and maybe middle school kids, in order to get them thinking about science and thinking about computers and programming, because it's very easy to use, and even if you don't have a lot of technical know-how, you can still throw something together that actually looks pretty nice. So it is graphical, and so the way we're going to write a program is that we're going to just use pieces, basically like puzzle pieces, that we're going to just drag them together. And this will make more sense when we do it, but if we want something to move 20 steps to the right, we're just going to grab a piece that says move to the right by 20 steps, and it's going to do that. So it is a real programming language, I should say, right? And in fact, what happens, I'll just say this probably once and not again, is that when we make our programs, they are translated into things that are more like the ones that I showed you earlier in this video. In other words, first maybe translated into sort of a mid-level language, and then ultimately translated into machine language or machine code, which, remember, that's zeros and ones. So I know we're not going to even type a single 0 or 1, but just so you know, the programs that we make, when we run them, believe me, are automatically, right? There's a lot of a lot that goes into this, but they are ultimately translated into zeros and ones that the computer that you're going to run this on is going to understand and say, oh, okay, this is what I'm going to do. I'm going to bounce this ball off the wall or whatever your game might do. So, and it is real programming, and people really do use Scratch for real life problems. Probably when it was designed, it was, as I said, designed mostly just sort of as a game building software for kids. But it has sort of taken off, and there's a very elaborate Scratch community out there that uses it to make games. For example, games you might have on your phone. And when you see, well, the website is down there at the bottom of the screen here. You'll see, sort of an entire community of people that use this and that study this and create amazing things using this very simple thing that you're going to learn in the course of a week and be able to make something hopefully pretty good. So this is the website. I mean, you can either type this in or just Google Scratch, and then maybe MIT is probably all you need to Google. This is sort of the main website for the whole community, I guess. This probably is more the website that maybe you want to click on first, which is going to let you download Scratch onto your computer. Now, somewhat new to Scratch is the ability to you don't actually need to download it. You can just use, when you click on this website, I'll show you in a second. There is a web-based version of it, which is sort of what they're directing you towards. And by that, I mean, you'd make all your stuff and then you would save it, but Scratch itself is not on your computer. You're just sort of logging in every time to the web service, more or less, and running it off of their servers. And that's fine. And if you want to do that, that's fine. Personally, I feel a little bit more secure in everything having a downloaded copy of the actual Scratch editor. So I don't want to tell you have to, but probably you're better off doing what I'm going to do right now, which is download Scratch onto your laptop, and then you'll have that program. And then the things you create, you're just going to create there. So in other words, you don't have to always worry about having to log on to the website to do stuff and all this business. So, okay, so if I click on this, oh, that's not good. um, oh, get out of here. Okay. All right. That probably will work when you click on it. So let me just grab it and paste it in. Okay, so anyway, hopefully that link will work when you go in there. But so this is the website that link takes you to. This scratch.mit, and then Scratch. There's a 2.0 version of Scratch, so everything will be called Scratch 2 instead of just Scratch. Download. Again, you can probably just Google download Scratch MIT, and I'm sure it'll take you to this very page. So as you can see here, a couple of things. One is that there's sort of three areas here. First, it uses Adobe. So if you don't have the latest version of Adobe, you should probably go ahead and update that. I don't know. I'm not up to date with exactly when these things came out, but if you do regular updates of Adobe, you're probably okay. But if you don't, or if you haven't, you click download to grab the latest version of Adobe and install it. If you have a Mac, you probably just want to hit right here. If you have a Windows machine, you probably want to hit right here. So do that. You might have to do a restart of your computer. And then after that's done, come back here again, and then download. This is the actual editor here. So this is the actual Scratch, which is officially, I guess, called the Scratch Offline Editor. So again, do the same thing. If you have a Mac, click here. If you have a Windows machine, click here and install it and open it up. And before I click off of this website, let me just say the third thing that's here are some projects, right? Some sort of examples. There's a guide here too, and some scratch cards. I think are little sort of study tips if you're. So probably don't click on that, but but there are some samples here. And if you just go to the general, I will click off this now and just hit Scratch, which is the Scratch homepage that I mentioned earlier. As I mentioned, there's a whole community here, right? There's what 18 million programs or projects, as they call them, and some of them are sort of featured here of things games people made, right? So, for example, if I click on this one, what you'll see is that this, right? So this screen, this is a game someone made, right, and uploaded here, and this is exactly how our screen's going to look. And just to give you a sense of what you can do, this is not a super advanced game, but if I play it, there's some music, and there's a little intro screen, and you can say, I can click on directions for how to play, which has some typos in it. Right, so okay, this is not too complicated a game, so then I can try it. So I can start. I think the objective of this game is to just avoid the red things. It's pretty easy to do most of the time. If I hit up, and it sort of returns me back to the beginning. And if I'm not great at it and I die, it takes me to some sort of you died screen, right? Okay, probably nobody's going to pay. Lots of noise. So okay, is somebody going to pay lots of money for that in the App Store or in a Google Play Store? No, right? Nobody's going to pay probably for that game. But this is the level that we're gonna come at, which is making a game though that if I kept playing that game, I'm sure it would get harder and things like that. But it's pretty neat, right? And I mean, whoever made that probably is like a 12-year-old or something like that. It actually is challenging to make a game even just that simple. But these are the sorts of levels of things that you're going to be able to do pretty quickly, I think, just by doing a few simple demos, which I'm going to record videos for, and then getting oriented with it. So anyway, I think that was the end of what I wanted to. Oh, no, it isn't. Okay. So download that. Oh, let me go back to this and finish this up here. So again, click on this link, or if it for some reason isn't working, just cut and paste it, or just Google Scratch MIT download. And then, yes, first install the latest version of Adobe, and then you should be able to install the editor, as it's called, which is that interface that we're gonna see when we open it. Okay, so you don't have to do that right now, but do that sort of as your first step. So I'm just going to finish these few slides, which is an orientation to using Scratch. So when you get there and when you look at Scratch, it'll look something like this. Now, as you can see, maybe if you have really good eyes, you can see the version of this that I have is not the 2.0 version; it's the 1.3 version. So, okay, when I made these slides several years ago, this was the current version. I promise you, the version you're going to look at is very similar to this. So. I believe they've moved things around a little bit, so I think this is on the left, and this is in the middle, and this is over here. Okay, but it's the same general idea. So this is the Scratch interface, or this is the Scratch editor, you might say. So just a little bit about what you're looking at here. So there's 4 zones, and again, even though they're moved around a little bit, the 4 zones that are going to be on your screen are the same. There's an area... so I should say, what's the premise for Scratch, right, as a language? So the premise for Scratch is that, as adorable as it sounds, is that you're going to put on a play, right? You're going to put on a show. So you have to kind of think again, like sort of elementary school or middle school, where you say, okay, this area over here, which maybe I'll go over here first and say, this area over here is called the stage. So this is where, and this is what your game or your story is going to actually be involved and is going to play out, is right here on this so-called stage. Okay. Now there's also, there are also characters or sprite, Scratch calls them sprites. So these are going to be the characters in your story that's going to be up here on the stage. As you can see, there's a cat right now. Cat, as you might imagine, Scratch, right? So that's why it's a cat, is the logo or is the icon for Scratch. So right now, this cat is the only character in the story. So this sprite, the cat, is the only one in the character list, and he's the only one on stage. Well, what else do you need to tell the story? You need scripts, right? So if you're going to put on a play, you have to put here what are called scripts, right? Which, like it would be in a play, is what's supposed to happen, right? Right now, there's nothing here. So this cat, who's a character or a sprite in this performance, it needs a script in order to say, well, what am I supposed to do? Oh, I'm supposed to run to the right, or I'm supposed to jump up and down, or whatever, right? That's going to go right here. And what are the scripts made of? These things. So these are the most important, this is the most important area called the blocks, or the block palette, where here's where we're going to grab, as you can probably see if you can read these pieces here. These are these puzzle pieces that I referred to earlier, which, as you can read just from these few that are at the top here, move 10 steps, turn 15 degrees, right? Move 10 steps, turn 15 degrees one way or the other, point in some direction, go to a spot on the screen, glide to a, okay, whatever, right? These, as you might imagine, are things you could say, oh, that's what the cat should be doing. The cat should be moving 10 steps, or the cat should be whatever. So all I'm going to have to do is grab, whichever of these pieces I want, pull them over here to write a script for the cat to perform. All right? So that's the general setup. Again, these things are in slightly different places in the current version. But these are the four kind of areas, I guess, that are going to be part of our experience. So, I think I probably said most of this, but here's what we're going to try to do, right? We're going to drag blocks from the palettes, from the different palette screens, to create scripts that are going to manipulate the characters or sprites in our story. Okay? Now, the types of script blocks, right, that we can use are broken up into a bunch of categories. Now, again, I think more or less the current version has these same categories. They may have 10 categories instead of 8. But anyway, each type of block or each type of thing you might want to do hopefully naturally falls into kind of one of these categories. So as you might imagine, motion, for example, if I click on that, will be the things that move the sprites, the characters. If you go to the Looks tab, this is going to be how you might change the appearance of the sprite. If you want sounds or music, you're going to probably hit the sound, and so on and so on. All right? You can draw. You don't use this a whole heck of a lot, but there is the ability to sort of draw on the screen. Sensing is probably not something you're going to do, again, a whole lot of, except for just basic things. Control is really important. So control is how we're going to sort of say, when should I do things? Well, as you might imagine, that's kind of important. There will be some math that we might do, and by that I just mean basic things like asking or checking if things are greater than or equal to or less than or whatever. And then sometimes we might need some variables to hold values, and that's going to be this tab. All right? So how do I kind of pull all this together, right? So the idea is that I'm going to take, if I want to say this is what you should do, this is your script, is I'm just going to grab some pieces. I mean, I'm going to pick the right ones or the ones that I want. And when I grab them, I can't do it here in the slide, but in Scratch you can. You can just pull and drag these pieces together, and they're going to click. You can probably sort of see, right? This, they're all sort of connected via these little cutouts, right? So I could snap these pieces together to make a 5-piece block, I guess, which would read or which would play from top to bottom. The character would say hello, then it would move 10 steps, then it would wait for a second, then it would go to where the mouse is, and then it would increase its size, I guess, or blow up or something like that. Okay, so that's how you build up. And I mean, how easy is that, right? It's going to be pretty simple just to grab these things and put them all together. Now, you're saying to yourself, well, what if I don't want the character to say hello and then move 10 steps and then wait a second? Okay, well, so you have to pick the right actions that you want it to do. But in terms of actually sort of pulling our program together, it literally is as easy as just pulling these pieces and snapping them together in the right order and all that good stuff. Okay, some things I just want to also point out, which maybe is self-explanatory. Most of the blocks, many of the blocks, sort of have options, right? There's going to be some things that are sort of set in stone, and then other things like numbers in many of these cases that are going to want to know a value, right? So for example, move 10 steps, obviously I could probably click on that and change it to a different number. Or you can even just put a variable in there that would say move, a variable named number of steps. So, right, so as you can see, wherever there's room for it, you're going to probably fill in numbers, or in this case, words that make sense to you, right? And this is where you can probably vary. You're gonna have to do a little bit of playing around. So what does 10 steps mean? I don't know, right? How far is 10 steps? Well, try it, right? You'll try it and say, oh, I want the character to move more than 10 steps. 10 steps was mini. So it's okay, fine, change that number to 20 or 30 or 100, whatever seems to make sense, and just keep trying. Okay? And sometimes you're going to get the numbers that you might put in these spots. You can see the type of opening or the type of space here is sort of an oval, right? It's sort of the same for all three of these, which means it wants a number. So you can either type the number in like was in the last slide, or you maybe need to do some math, right? And say, oh, you know what? The number that's going to go in there is actually some other number plus some other number. Or maybe you're going to use a random number. So one of the requirements of the game, like any game, is that you have randomness. Right? So maybe instead of saying move 10 steps, maybe I'll say pick a random number between 1 and 10. Oh, okay, so that means every time I do it, I might move a lot or a little. Okay, that might be useful. Now, other openings that you're going to see in some of the pieces are, what is this, a hexagon maybe? This shape, whatever that is. These are looking for true false, or as the fancy word for that is Boolean, or we would know this as binary, right? So some pieces are looking for numbers, like I would put is 4 less than 7 or something like that, right? But other pieces are looking for true false statements. So I might say, is this and this true? Notice, actually, these three that I picked out here are just our logic gates, right? So we used the AND gate to say, A and B, or not A, or B, or, right? So those guys are still here. But the point is that what are the types of things we're going to put in here to ask the question, are these both true? Or maybe some questions, and these are all built into, like, am I pressing the right arrow? Is the mouse clicked? Is the object touching an edge of the screen? So these are all yes, no, or true, false questions. So I could put them naturally into these sorts of places in order to say, oh, if the right arrow is pressed or the mouse is down, then do some stuff. Now, where are those guys, these green guys, for the most part, are going to probably be plopped then into something like this, where it's like, okay, so if the mouse is pressed, or if it's touching the edge, then do some stuff. So these are called control pieces. The orange pieces are called control pieces. And I'm going to sometimes have a need to ask conditional statements. So conditional statements mean, just as it suggests, I'm waiting or I'm looking to see, is a condition true? And if it is, then I should do some stuff. So I might say, if it's touching the edge, move 20 steps. Which goes to say, okay, so if it isn't, then I'm not going to do that. Okay, there's a lot of control, which are all these orange pieces that you're going to see. Those are really important. That's where you're going to have some, I don't want to say difficulty, but that's where there's going to be some challenges. Well, what kind of how do I describe when I want this to happen? Can be a little bit of a challenge. So. There's a variety of ones to pick from. You can pick you'll use probably quite a few of these ifs, right? So the idea here is that it's saying, if this is true, then do this, and then move on. A variation on that would be to say, you could ask, if this is true, do some stuff. Otherwise, do this stuff. So this is called an if-else. And what that just means is that if you want to ask yourself something like, well, if the score is more than 10, do this. Otherwise, do that, is how I might read that. I didn't realize I had an example here, right? So if the mouse is pressed, then play this note. But otherwise, play the drum for 0.2 beats. Okay, so you'll use these if conditionals and if else conditionals quite a bit. Some other ones, and I'll show you all these in action, but another one that's very useful is forever. So there's another one of these orange pieces called forever. What that's going to encapsulate for you is the ability to say, keep doing this, or keep checking this, or keep whatever as the game is going on. So you might always want to be checking, if your score is 0, you want to end the game. So that might go inside of something that's going to say, and keep doing this, right? In other words, do this forever, not just once or twice. Okay, but we'll get to those. So as a last slide, I'll just say, right, you can make very complicated games, even something like Tetris or some sort of other sort of block stacking type of a game using Scratch, and it's not even that crazy to do. So you can do a lot, right? And just to sort of show you, right, that this is what I mean when I say you're just going to grab pieces and put them together in order to say, oh, okay, that's what this should be doing right now. It should be whatever all these commands might be here. And it is pretty powerful, and you can make something that's actually pretty cool that you'd want to, show your friends and be like, ooh, play my game, sort of things. So, all right, well, I'm going to stop this video. So if you haven't already done so, do this. Go to the download page here. Download Adobe, download Scratch. You might need to do a restart of your laptop, maybe after you do step 1, and maybe even also after you do step 2. But hopefully you can download Scratch, get it on your computer, and that way you'll have it there, and you can use it to do any of your editing without having to go through the website every time. So the next video, I'll open up Scratch, and we'll make our first mini game, or our first mini, not really game, but our first program together.